Right. So in question 43, the first bit says W adiabatic and W isothermal. For the comparison, we'll just draw P versus V graph. Now you have the same initial state and there is a compression till you reach the same final volume. Let's say this is the final volume that you want to reach and this is the initial state. Now adiabatic curves are steeper than isothermal plots, so this would be an adiabatic plot and this is the isothermal one. Area under the graph is greater for the adiabatic one, so work done for the first bit will be greater. Work done for adiabatic process will be greater. The second option B says the value of gamma remains constant, and this is not true. This is not true because at higher temperatures, vibrational modes of freedom become active, and the value of gamma will change accordingly. Option C says entropy increases when ideal gas expands isothermally. Yeah, that's right. For an ideal gas, for any gas, in fact, delta S can be written as NCV ln of T2 by T1 plus NR ln V2 by V1. This is true for ideal gases, not for any gas, but for ideal gases. As you can see, as long as T2 by T1 is greater than 1 or T2 is greater, delta S will have a positive sign because of it. Same thing goes for volume as well. So entropy will increase both with increase in temperature as well as increase in volume. In this case, volume increases, so entropy increases as well. As for the last bit, magnesium carbonate on heating decomposes to give you magnesium oxide and CO2. Because you have to heat it, we know for a fact the delta H is positive. Also, 1 mole of a solid breaks down to give you 1 solid plus 1 gas. So delta S is positive as well because of increase in randomness due to gas formation. The next question is question 47. First statement says due to an adiabatic free expansion, temperature of a real gas always increases. Okay, now that's not true. This is in fact a portion from real gases. We dealt with something called inversion temperature. There you have it. Now, according to Joule-Thomson cooling effect, if a gas undergoes certain expansion, then it undergoes cooling, which is a general observation as well. You've seen it when you blow onto your hand, it feels cooler. But if you, let's say you yawn and place your hand near your mouth, you'll see that the air which is coming out is actually warm. Anyways, Joule-Thomson cooling effect says this, that if a gas suddenly expands from a region of high pressure to a region of low pressure, that causes cooling. But that only takes place till inversion temperature. Now, once the temperature is above inversion temperature, the opposite effect kicks in. That is, expansion will cause the gas to heat up. Now, when they are at inversion temperature, there is no change in temperature. At inversion temperature, expansion neither heats it up nor cools it down. So the first statement is incorrect, whereas the second statement is correct. Right? Yeah, second is correct. Okay. Now we go on to this paragraph, the comprehension question. Right, the comprehension question says, okay, we have initial volumes of 22.4 liters each. This is adiabatic. The right container is adiabatic, whereas the left container, you're heating the gas in the left container in section A. So as you heat it, pressure in this section builds up. And as a result, this will force the piston to compress compress the gas in section B as well, so that at the end, the pressure in both A and B will be same. That's always the condition for a mechanical equilibrium. Pressure cannot be different across a movable boundary. So if the initial volume was V, which is 22.4 liters, actually given as well, this final volume is 1/8 of the initial volume. It's V by 8. right? And this process is adiabatic. It also says that it is either reversible or irreversible. You have to look for that. Okay. It's reversibly heated, so the process is reversible in nature. Now, question 48 is what would be the final pressure in container B? To find out the final pressure in container B, we know this is a reversible adiabatic process. So we can use the equation P1 V1 to the power gamma is P2 V2 to the power gamma. P1 is, both have 1 atm. Yeah, so P1 is 1 atm. V1 is V. It's a monoatomic ideal gas, so the value of gamma is 5 by 3. That is equal to P2 into V by 8 to the power of 5 by 3. You can solve. You can solve for P2 using this. Right, so that would be 2 to the power 5. P2 is 32. 32 atm. Yes. Right, now the question 49 says find the temperature in container A. Okay, for the container A, you know that the final pressure PF, or let's call it P2, that is 32 atm. It has to be same as in container B at that particular stage. And you want to find out the final temperature in container A. Right, so pressure is known, temperature is not known, number of moles I think that is known. Yes, the initial conditions are given. You have 27.3 Kelvin, 1 atm and a volume of 22.4 liters. So the initial moles are 10. The volume has increased. It was initially 22.4 liters. Now it has increased by 7/8 of the volume of the gas in container B. B has shrunk to 1/8 of its volume, so that 7/8 of the volume has been transferred to the chamber A. Right, there you go. This many liters. So that helps you calculate temperature. Now once you find out the final temperature, the change in enthalpy can also be calculated. Right. Okay. Now the next comprehension is comprehension 2. It says an ideal gas is expanded so the amount of heat transfer to the gas is equal to decrease in its internal energy. Okay, so the general equation is Q plus W is equal to delta U. This is minus of NCV. No, delta U is NCV dt. Differential form. Okay, just a second. It says that the amount of heat added is equal to decrease in internal energy. So dq is equal to minus of du. And so minus of du plus dw is du. This is given. So you can write that dw is twice of du, or this is twice of n cv dt. Now dw can be written as a minus of pdv, which is 2n cv into dt. Now, see, this equation is familiar. This is equivalent to, this is similar to the derivation for the equation of state for an adiabatic process. Instead of P, because in ideal gas, you write nRT by V. So, R by 2 CV divided by 2CV into dV by V is equal to dt divided by t. This comes with a negative sign on this side, so you integrate this. Integrate this from the volume, let's say V1 to V2, and the corresponding temperature limits on the other side T1 to T2. This should give you the equation between T and V. Okay, question 53 says find what is the magnitude of work performed by 1 mole of a gas when volume increases 8 times if the initial temperature of the gas is 300 Kelvin. It is an adiabatic process. Right, for work done, right, see this is what we can do. For work done, you already know dW is equal to twice of du. Use this part of the equation, and twice of du can witness twice of n CV dt integrated. CV is constant, so twice of n CV dt, so W becomes twice of n CV delta T. We need to evaluate delta T to get the answer for work done, and to evaluate delta T, you'll have to use whatever equation of state you get from this. This equation of state has to be used here. That equation of state can be used because you know the initial temperature T1 and the initial volume becomes 8 times. So if you use the equation of state there, you can calculate T2. Once T2 can be calculated, once T2 is found out, you can calculate for delta T, and that will help you solve this question. Okay, so this is the last doubt in this section. This is 58. For the process A liquid to A, delta H and delta V may both be. Okay, so for the first bit, as you go from a liquid to a solid, solidification is taking place. Fusion is the opposite of melting, rather. That's solidification is taking place. So delta H there has to be negative, cannot be positive. But the value of delta V could be negative or positive. Either would work. For the second bit, A2 plus B2, see, one solid and one gas gives you one solid plus one solid. So we know that for this process, delta S will be negative because the number of gaseous moles are decreasing. So delta S is negative. So delta H could be either positive or negative. Now the sign of delta G will depend upon these. Delta G is delta H minus of T delta S. And because it is minus of T delta S, this part is positive. So if delta H is negative, then delta G could either be negative or positive. But if delta H turns out to be positive, then delta G has to be positive as well. So we can have negative, negative as one possibility, negative. We can have negative, negative as one possibility, negative, positive as another possibility, and positive, positive as another possibility. You cannot have the combination Q, it cannot be positive and negative. For option C, says activation energy forward and backward. So delta H is EA forward minus EA backwards. So that is plus 10 kilojoules per mole in this case. So delta H can only be positive. At a very high temperature, delta G is delta H minus of T delta S. This is a small number, this is plus 10. And as you can see from the equation, one gas changes into two gases. So delta S is positive, which means minus of T delta S has to be negative. And at very high temperature, minus of T delta S should overpower delta H. So delta G should be negative as well. So in this case, this has to be positive and delta G has to be negative at low temperature. Option D, delta S, we can't exactly say it is equal to 0, but it will be a very small value, either a small positive value or a small negative value. Delta H and delta G. Delta H, I don't know. Delta H can be positive. If delta H is positive, delta G is mostly also positive because delta G is delta H minus of T delta S. The second term is nearly 0. So the sign of delta H and delta G have to be same. So if it is positive, delta G should be positive. If this is negative, then delta G should be negative as well.